Hello. In the last video, we talked about the fact that certain kinds of molecules are called chiral, and if a molecule is chiral, then that means it's not the same as its mirror image. So there should be two different molecules with the same structure, but mirror images of each other, and if so, then they are called enantiomers. You can recognize mostly a chiral compound by the fact that it will have one, or in some cases more, than one chiral carbon. And this is a chiral carbon because it has four different groups attached to it. It's not just four groups, but four different groups. This has the same four groups, but arranged in such a way that it's a mirror image of this one. And notice that this one cannot be ever this exact same as this one. In other words, they are not superimposable. So, does that mean that in reality there are two different forms of some compounds? And the answer is absolutely. For example, a compound called 2-butanol. That's the name of this compound. In the last video, I referred to it as sec-butyl alcohol. Also, neither one of which do you need to know at this point. We will learn about naming alcohols later on. That's what this is, but notice that this carbon is a chiral carbon because it has four different groups: a hydrogen, an OH, a methyl, and an ethyl. So this is a chiral carbon. That means that its mirror image should be different from it, which means they are both chiral. So the question is, do they both exist, and what about their properties? Are the properties of this different than the properties of this, or not? Well, the answer is yes, there are two different compounds of that structure. They are mirror images of each other. They're called enantiomers, but here's their properties. Notice that this compound has a melting point of negative 114.7. This one has a melting point of negative 114.7, same melting point. This has a boiling point of 95.5. This has a boiling point of 95.5, same boiling point. This has a density of 0.806 grams per milliliter. This has a density of 0.806 grams per milliliter. Get the idea? Their properties are the same, almost. Refractive index 1.398, refractive index 1.398. So they are the same in most ways. However, notice there's something called optical rotation, and we'll talk about what that means and how you measure it here in a minute. But it has a value of negative 15 degrees for this compound, positive 15 degrees for this compound. So the same number, but opposite signs. This one, if it were to react with an achiral molecule, like for example water or methane or some other compound that is not itself chiral, it would react in exactly the same way as this compound would with that same achiral molecule. They react identically as long as the compound that they are reacting with is not chiral itself. However, if this were to react with minus 2-bromobutane, which is an enantiomer of plus 2-bromobutane, so that means this is chiral. If this were to react with it, it would be different from the way this reacts with it. So they react differently as long as the substance they are reacting with is itself chiral. Now let's go back to looking at these two compounds. First of all, be aware that these two molecules can occur in a number of different mixtures. Could be that you have a sample that's 100% of this. Could be that you have a sample that's 100% of this. Could be that you have a sample that's 50-50 of these two, and if so, that's what's called a racemic mixture. This word R-A-C-E-M-I-C. Actually, that word comes from the genus name for grapes, which is interesting, but nowadays racemic just means 50-50 mixture of two enantiomers. But you can also have, say, 25-75 mixture, or 10% and 90%, or some other combination. There's no reason why they have to be in any particular ratio with each other. Although normally in the laboratory you tend to get racemic mixtures, 50-50 mixtures of things. Normally in nature, if you have a chiral molecule, you generally just get one of the two enantiomers of it. Also very interesting fact, we'll talk more about that later as well. So question, if you had a 50-50 mixture of these two, could they be separated from each other? Could you boil them apart? Nope, same boiling point. Could you crystallize them apart? Nope, same solubility in whatever solvent you might choose. Unless the solvent itself were chiral, which is an interesting thing. But basically, it's very difficult to separate them from each other unless you react them with another chiral molecule. And that is a process called resolution. In fact, you will be doing a resolution in the laboratory where you'll take a compound that's a 50-50 mixture of two enantiomers and you'll separate them by reacting them with something that's already chiral. In any case, let's talk about how we categorize these. This one happens to be, and I only know this because I looked it up, the negative or levorotatory isomer. If we go back to the previous slide, you will see that this one has a negative optical rotation. And that's also sometimes given as an L. That's a small letter L. It means the same thing as negative. And the word we use is levorotatory, which means rotating to the left. So the rotation will be counterclockwise. This is called the plus or dextrorotatory, meaning it rotates like to the right, sometimes called the D for dextrorotatory. So plus means the same thing as small d, minus means the same thing as small l. Now here's a question. If we know the optical rotations of one set of enantiomers, and we do know that this one is negative 15 and this one is positive 15, and again I know that because I looked it up, can you then predict what will be the optical rotation of this isomer and what will be the optical rotation of this isomer? And the answer is no. Not only do we not know what the number is, this could be 15 or 30 or 0.2 or 1.78 or who knows what the number is for this one. Whatever it is, it's the same for this one, except one of them will be positive and the other one will be negative. Do we know which one's positive and which one's negative? Well, this one looks kind of like this one, so maybe it's negative. Nope, doesn't work that way. You cannot predict, just by looking at the structure, whether a particular enantiomer will be the dextrorotatory or the levorotatory isomer. Now, here we're going to talk about what is optical rotation. Well, first of all, let's talk a little bit about light. You know that light, when it's coming out of the sun or one of these fluorescent bulbs or in the window or whatever, is vibrating. So it's vibrating in a plane like this. It's also vibrating in a plane like this, and like this, and like this, and every other direction. That's what this little star represents, is light vibrating up and down, side to side, at an angle this way, at an angle that way, and all other angles in between. So what we do then in a polarimeter is we pass that light through what's called a polarizer. Well, a polarizer is really just a piece of material that has lines in it, all parallel to each other. Now, do you remember the diffraction gratings that we used when we looked at the gas discharge tube showing us the spectra of various elements in general chemistry? Well, those were actually polarizers. The little diffraction grating is a polarizer, which means when the light passes through that diffraction grating, if it's vibrating this way, that's fine, it passes right through. But if it's vibrating this way, it gets blocked, it doesn't go through. Or if it's vibrating this way, it gets blocked. So basically only light that's vibrating in a particular plane will get through, and that then is called plane polarized light. So that's to represent, this right here represents the plane polarized light. Notice that instead of vibrating in all directions, it's only vibrating in one direction. Then at that point, the plane polarized light is passed through a tube, and in this tube will be a sample. It may contain one or the other or both enantiomers, maybe a racemic mixture 50-50 or maybe some other mixture, but it contains a mixture usually dissolved in some sort of solvent and usually 10 centimeters long. That is 1 decimeter. Now, a decimeter is not a unit that we use very much, at least not in general chemistry, but for some reason the tube they use in these instruments is almost always 1 decimeter long. Sometimes they use a 2 decimeter tube, but I happen to have here a 1 decimeter polarimeter tube. Notice that it's got windows on both ends, so light is going to pass through the sample and then go out the other side. And we can take the cap off and we can put our sample into the tube, put the cap back on again, and now we have the tube. What we're going to do then is put that tube into a machine called a polarimeter. So drop the tube in, we're going to close the window, and if we were actually doing an experiment now, I would turn on this right here. This is a lamp which generates a kind of light that's monochromatic, meaning it's just one wavelength. Most of the time what we use is the kind of light called the D line of sodium. So this is a sodium lamp in here. It has different lines in its spectrum. The D line is the bright yellow line of sodium, and that's what this lamp generates. That light's going to be passed through here, through a polarizer at this point, passes through the tube, and then goes to the eyepiece. We're going to look in here, and when we do this in the laboratory, I will show you how to actually read the polarimeter. But basically what it's going to do is tell us, after the light passes through the tube, it's going to go to this thing called a polarimeter, and it's going to measure how much has that angle changed as it went through. So it starts out this way. As it passes through the tube, it rotates one way or the other way. If it rotates to the left, it's called levorotatory or counterclockwise. If it rotates to the right, that's called dextrorotatory or clockwise. This is just a blown up picture of what I showed you a minute ago. You can take a look at it and see if you can get the idea of what it's talking about. Now, how do you actually measure it? Well, like I said, I'll show you the details of how you read the instrument in the laboratory when we do this experiment. But let's define some terms here. First of all, what's called the absolute rotation is the Greek letter alpha in square brackets and then little letter d. So that's the number that I showed you before, the negative 15 for L2-butanol. That was the absolute rotation. That's the number that is a constant and should be the same for anybody that measures that compound, as long as it's just the L isomer. It's 100% of the L isomer. This L here has nothing to do with levorotatory. That's the length of the tube. And obviously that matters when you measure it, because if you let the light go through a short tube, it's not going to rotate very much. If you get it go through a longer tube, it's going to have more time to rotate. So we have to take into account the length of the tube. And then there's this C, which is the concentration. And that's the concentration of the solution you put in. You remember I said a minute ago, generally you don't put a pure compound into the tube, you put a solution with some solvent. Normally that solvent is ethanol or sometimes methylene chloride, but it's just a typical solvent of some sort. But you have to measure how concentrated it is, because if it's very concentrated, it's going to rotate light faster. If it's not very concentrated, it's going to rotate light slower. So obviously the concentration matters, and you need to know that as well. So here's the formula. It's a pretty simple idea. And by the way, the capital D means that we're using a wavelength. It's the D line of sodium. This is the observed rotation, so whatever you get off of the instrument you put there, you divide it by the length of the tube, and that's in decimeters. And again, since it's usually a 1 decimeter tube, that factor kind of drops out. And then this is the concentration in grams per milliliter. Now you might wonder, that's kind of a funny concentration unit. Why do we not use molarity, which seems to be the one we use most of the time? And the answer is because to calculate molarity, you need to know moles. And to get moles, you need to know the molar mass. Sometimes you want to take the optical rotation of a compound. You don't know what it is. You know what its molar mass is. You can't calculate moles. So we put the concentration in grams per milliliter instead of some other one that depends on moles. So here's a problem for you. Let's say you did an optical rotation or you did a polarimetry experiment on a sample of 2-butanol. It had a concentration of 0.345 grams per milliliter. In the solution, you put it into the tube, in a 1 decimeter tube, and you measure the rotation to be minus 3.1 degrees. The first question you might ask is, why isn't that minus 15? Because we saw a minute ago that it has a rotation of minus 15. 2 reasons. First of all, because we haven't done this calculation yet. And secondly, because it might not be pure. I mean, only if there's just one isomer will it be minus 15. So first thing you have to do is calculate what is the specific rotation. If the observed rotation is negative 3.1, the length of the tube is 1 decimeter, and the concentration is 0.345 grams per milliliter. You can do that calculation, take a minute and do it real quickly. And next slide, I'll show you the answer. Here we go. So you're going to take the observed rotation, negative 3.1, divided by the length of the tube, which is 1 decimeter, and the concentration in grams per milliliter, which is 0.345, and you should come up with an answer of minus 9.0 degrees. Again, you might say, well, why isn't that negative 15? Because we saw a minute ago that it should be negative 15. And the answer is because obviously then this is not pure 100% of the negative isomer. There must be some of the positive isomer in there as well, which is making it be less negative than it should be. So here's where we figure out how much of it is negative and how much of it is positive. What we saw a minute ago, as I said, was that pure negative 2-butanol should be negative 15, but the sample in this case turned out to be negative 9. So what does that mean? Well, first of all, it means the sample's not racemic, because if it were racemic, the optical rotation would be 0 degrees. In other words, if it's 50-50 of the negative and the positive, the negative is trying to turn this way, the positive is trying to turn that way, it would go through unchanged. So the absolute rotation would be 0 degrees. But it's also true that it's not optically pure, in other words, not 100% of the negative isomer, because then it would be negative 15 degrees instead of being negative 9 degrees. So then what we do is we calculate something called the optical purity. Sometimes this is referred to as enantiomeric excess. So optical purity means the same thing as enantiomeric excess, and I'll explain why here in just a minute. But the calculation is that you take the number you get divided by the number you should get. In many ways, it's just like a percent yield calculation. You take the grams you do get divided by the grams you should get, and that gives you your percent yield. Well, this is you take the rotation you actually get divided by the rotation you should get, and you get a percentage. So in this case, it turns out to be 60% optically pure. Now, what does that mean? Well, that means that 60% of it is the minus isomer, because it's obviously more negative than positive, because the answer came out to be negative. So it's 60% of the negative enantiomer. What's the other 40%? Well, the other 40% isn't the positive isomer. The other 40% is racemic. So it's 60% pure negative and 40% racemic, which means, of course, that that 40%, half of it, or 20%, is also negative, and the other half, or 20%, is positive. So in total, it's 60% negative plus 20% negative, and then 20% positive. So 80% total negative, 20% total positive. So the enantiomeric excess, in other words, the amount of that enantiomer over what it would be if it was racemic, is 60%. And that's what you get by taking the actual divided by the theoretical number here. Now, here's something to notice. If it was a racemic mixture, you might say, well, that should be 50% enantiomeric excess. But of course, it's not. If it's racemic, it's 0% enantiomeric excess, because it is racemic. It's 0% above racemic. And that will be the end of this lecture today. Thank you.